So let me begin by thanking the organizers. I first visited 2015 for a conference, and then after 10 years, it is nice to be here again. And I will talk about two models. One is an extended SSH models, and then its extension into dimensions. This work is based on these two works in collaboration with my colleague Arijit and my postdoc Hemant Kumar, and the second was with my colleague at Niger, friend Kusa. So let me, this is an exact calculations, not very difficult calculations, but what's new? Because we know that SSH model has been proposed in 1960s. It is almost 60 years. So the SSH model is a nearest neighbor hopping model that we all know probably, and it is having a kind of dimer systems. We have two different kind of hoppings, which is, let's say, the inter-cell hopping, which is intra-cell hopping V, and then inter-cell hopping, which is W. So when one plays with this V and W, one can see interesting topology of the systems. For example, when one of the hopping is greater than W, then the system would have finite winding numbers. Depending upon how you cut the systems, you can have a edge modes. So now our question was that this SSH model is a spinless model. That means spin component here is suppressed, and we can think about that if we take the same model for upspin or downspin, it does not matter. And now we ask the question, can we for such a spin pool where it is just two copies of the SSH model, my topology of the systems will be same. For example, the topology of the upspin and topology of the downspin will be the same. And this model is just a 2 by 2 Hamiltonian matrix, and one can analytically calculate many properties. For example, when is the gap closing points, where is the winding number for which parameter regime, and etc., etc. So first our question was that if we take a proper spin full variant of this, can we independently vary the winding number or the topology of the two sectors of the SSH models. So this was our first questions, and whether we can get some of all those conditions analytically or not. So for this reason, let me skip the symmetry part. This is our the version of the SSH model. So we took the simple SSH model. This is the first part, and then we put a spin orbit couple like this. So what this spin orbit couple is doing, this spin orbit couple does a spin dependent hopping, but it does conserve the spins. That means it does not flip the spins. So I alpha R1, it is the intracell spin dependent hopping, same for the down spins. But for the upspin, it is with some I, and for the downspin with the minus I. So this is we call it a spin orbit couple, intrinsic spin orbit couple. And if you look at this and this, these two terms does not break the time reversal symmetries. Then we also added a spin dependent Rashba interaction. So that means when we have a hopping from A sublattice to B sublattice, then it will flip the spins. So this does not conserve the spins. So even these three terms does not break the time reversal symmetry. And even with these cases, we can have the topology of the two sectors same. So then what to achieve our final aim, we added a next to next nearest hopping B to A, which is actually the fourth neighbor. We did not allow any B to B because it breaks the chiral symmetry, and then we cannot have a quantized Jack phase. So we allowed a next to next nearest neighbor hopping gamma, and we also made the gamma to be, we realized that unless until we make the gamma complex, we cannot really vary the topological winding number different for different spin sectors. So, this is the main story of the problems, and basically analytically we found many conditions depending upon these things. So, what we found is that unless until when this term is 0 and this term is 0, we see that my 4 by 4 matrix, it is completely, let me show whether I have not probably put that in the slides. So, this is a decoupled system, that means the upspin sector and the upspin sector and downshift sector, there is no off diagonal coupling, and we can have exact analytical expression for everything. Now, when this spin orbit couple is there and this spin orbit couple is not present there, then we found that this term and this term, still one can do a basis transformations, and still one can do everything analytically. But when all these 4 terms are there, then it is a 4 by 4 matrix, and as we know that even the exact eigenvalues and eigenvector of a 4 by 4 matrix is not possible, but somehow using the theory of non-Hermitian matrices, we found exact analytical analysis of everything like gap closing point, where the topological transition will happen, and etc. So, this is the main result of the main result. And as it is a topological system, as we know that there will be some edge modes and etc. So, in next slide I will just quickly show our results. Then apart from that, what we found another very interesting, the effect of this next to next nearest neighbor hopping. So, recently there has been a couple of years back, there is one paper, as we know this SSH model, if one cuts with A sublattice this side and B sublattice this side, there will be 2 edge modes, which is the signature of the topology. Now, here V and W, they are periodic, that means this intercell hopping and this intercell hopping, they are all identicals. Now, if one varies this V, this intra-cell hopping such that they are varying little bit, for example, this V is as it is V now, but this V is little bit of less, V minus delta. So, now this V is, let us say, V minus 2 delta, this V is minus 3 delta, it gradually decreases, and this W somehow, this inter-cell coupling, this somehow increases little bit. Okay. So, what will happen that then this V is gradually decreasing and W is gradually increasing, and then at the end what will happen, like this V will gradually decrease and then change sign like this, and this W, it will increase its sign and then gradually go like that. So, then this is called exactly the domain wall potential. So, under this domain wall potential, what happens is that this left edge states moves and goes exactly at the center of the one dimensional open chain. Okay. So, then very interestingly what we found that when we allow this next to next nearest neighbor hopping gamma, then this location of the domain wall, in the presence of domain wall, the edge mode which was exactly sitting in the middle of the my finite size system, we can actually manipulate its localization. Okay. Now, let me go through a little bit faster. This is the main result, and these are we can look at you can look at our paper for more detail. For example, what we have, this is the gap closing point when one of the we put the Rasba interactions, and then what we found is that in the presence of all these parameters V, W, alpha 1, alpha 2, alpha 3, alpha 4, this gap closing point can be nicely put in a this kind of equations, where my V is now a vector given by V alpha and alpha 3. So, it will be alpha 1, and W is W alpha 2 alpha 4, and they nicely give a equation like that in the V alpha 1 alpha 2 parameter space. And also we found that when this next to next nearest neighbor hopping is present, we can have a anisotropic Dirac point, and we will show some plot for that, and our analytical calculation give exact expression for the winding number. So, one useful way to analysis SSH model is that you find the diagonal off diagonal Hamiltonian parameter, and as a off diagonal parameter, when it encloses the circle or not, then it indicates a finite topology or not. So, this is some representative figure for that, and this is a, let me skip the main result. This is the where how the gap closing point k varies with a different parameters. This is the plot for that, and let me spend some time here. So, what happens when we all put one by one each parameter. So, this figure A shows our simple SSH model, where we have taken some parameter probably V greater than W. Yeah, we have taken W to be 0.9 and V is probably taken 1 for all panel. So, here both the spin sectors is identical because it has no other parameters. Now, here we have substituted, we have turned on only alpha 1 and alpha 2, that means the Rashba spin orbit couple which conserve the spins. So, we see that the bands become degenerate for up spin and down spin, but still there is a time reversal symmetry. For example, this point can be mapped to this point and this point can be mapped to this point. For up spin energy can be mapped to the down spin energy. Now, on top of that, when we add a alpha 3 alpha 4, this is a band crossing. This band crossing now turns into a band touching points, and actually we find a one dimensional Dirac nodes at finite energies. Now, on top of that, if you add the next to next nearest neighbor hopping, then this Dirac point becomes asymmetric. So, and these are other parameters, we can play with the gap closing depending upon the parameters and etc. So, in short, we go from a degenerate band to non-degenerate band, but the key feature of the time reverse symmetry keeping intact, and then we again go from a Dirac nodes, and that Dirac nodes develops a asymmetry in the presence of next to next nearest neighbor hopping. Okay. So, this is to show that how I can when we have only one sector non-trivial topology, then we will have a pair of zero modes, mid gap energy zero modes, but when both the spin sectors will be topological, then we will have a two pair, that means 4 zero energy edge modes. And here we show how it can be varied from 1 to 2 etc. This is a phase diagram in parameter space. We have multi-critical topological phase transition points, and we also have a re-entrant topological phase transitions depending upon our parameters. Again, it is a repetition of that, and as we have alpha 3 alpha 4 which does not conserve the spins. So, here the edge modes will have a definitive spin structure, that means it will have a definite sigma x, sigma y and sigma z component. It is just a demonstration of that, how the spin components varies as we are going from edge to the bulk. So, then we asked another question, that if we couple such a chains indefinitely in y directions, what will be the criteria such that my winding number can vary from 0 to capital 2m. So, we have found that if we allow again a chiral symmetry preserving hopping, that means A to B and B to A, we can actually create as many as edge modes depending upon the number of chains. So, if we have, let us say 10 such coupled chains, my winding number can vary from 1 to 20 in steps of all integer numbers. So, W can vary from 0 to Tms, and this is a interesting observations. So, it is a for two coupled chains, the various fermionic sectors depending upon the values of W, how it acquires its non-trivial topology. It is a table of that. Let me skip this part, and this is also a phase diagram, and to show that how the edge modes can be arbitrarily created depending upon my parameter choices. And this is a 2-dimensional, when in the 2D limit, when such coupled chains acquires a finite 2D limit, then we wanted to see that how it develops. So, there are some this is a band diagrams and in kx as a function of koi, which is in my transverse directions. And as we did not allow any chiral symmetry breaking term, so the total Chern number is 0, and that's why we analyze this system with a Chern number only as a function of koi, and we see that when we have this is a here when we have chiral symmetry preserving term, we have exactly the Jack phase quantized, but when we allow a diagonal term which breaks the chiral symmetry, then we have a fractional Jack phase also. Okay. So, this is the domain wall potential that I was talking about, and in the presence of domain Wilson, one can calculate the spatial location of the edge modes analytically, but expression is not always possible. And here we show that how the domain wall can create the edge modes at the end, and it can actually vary the mid gap location of the mid gap. It is not very clear here. I will show a clearer picture. Let me as you see that it is away from the middle. It is little bit away from that. Maybe this picture is further better. For example, in ideal domain wall case, my mid gap location should be at the side of 200 if my system size is 400, but depending upon my various parameters, I can actually we can control the mid gap localization of the mid gap states. So, it can go from left to right as well also, as we see it can go from left to right etc. Okay. So, this is some calculation of the IPR and NPR as this topology in the presence of. So, we are more interested in the IPR and NPR because there is a little bit of history. So, there was a very recent interesting paper where this SSH model has been investigated in the presence of an Abreu-Andre potentials. As we know that Abreu-Andre potential is a quasi periodic potentials, and in the presence of that, what happens that the topological phase goes to a non-topological phase, and again depending upon your system parameters, again another topological phase reappears, which is called reentrant topological phase. So, this localization to delocalization condition is normally analyzed in the presence of IPR, inverse participation ratios, which is the power of the fourth power of the amplitude of a given wave function at a given site, and we sum over all the sites. So, this IPR in the presence of, our question was how the IPR varies in the presence of domain wall and Abreu-Andre potential both. We found some interesting result in some cases that I want to show you. For example, here where domain wall and Abreu-Andre potential is both present, in some cases the IPR shows some intermittent peaks. So, where we think that there is some the fractional states. Okay. So, now in there was a recent work where there has been interest to show that, for example, in spin orbit coupled systems, normally the spin is coupled to the momentum, and if we look at the kx ky plane, the spin is always as a function of the momentum. This is done with the Rashba spin orbit interactions. But if we now put a Dresselhaus, now the spins varies with kx ky like that. Now, if in your system Rashba and Dresselhaus both are present, then it shows that as a function of kx ky plane, the spin does not change. So, this is called the persistent spin structure, and it can have a interesting application in your technological technology. So, our model also shows that depending upon our parameters, this model shows a interesting region in the momentum space where this persistent spin structure happens, and this solely depends upon the parameter of the next to next nearest neighbor complex hopping. So, this is not much this is about the not much, and I can take questions now.
Okay. Thank you. We have time for questions now. So, this hopping terms that we included, taking in account that we don't want this chirality to break. So what if we take this, because if you compare the this hoppings, then the dominant hoppings seem to be the one that we neglected, because these are the nearest and the next nearest interactions or hoppings. So my question is that apart from this non-defining of exact phase, what effect can it have when we include this hopping terms which break the chirality? Is there any?
When the chirality is broken, then there is no invariant for the one-dimensional systems. Okay, so the topology is not defined. It will be go to non-topological phase because topological invariant is absent. But that's why in 2 dimension we have this 2-dimensional limit. We have now allowed this. We have allowed this nearest neighbor hopping, that A to A. Okay, and then we can define a Chern number, etc. And our 2D work, that 2D coupled chain paper, there we show that when we have the A to A hopping that we want to allow, then jack phase can be defined, but it will not be quantized. So depending upon how much, how large or how less is your that number, you can define, but it will not be quantized. You can define the topological invariant, but it will not be quantized. Like here we see it has some fractional values and etc. Yes, yeah, definitely. And I want to show that there has been recent one paper actually when we are dealing with the referee report. There was exactly a paper which has proposed a that topoelectrical circuit exactly given this model, that next to next nearest neighbor hopping with spring and mass systems. So though we can think about for the electronic systems, it is not possible. For mechanical system or artificial system, it is possible. We can avoid the next to next nearest neighbor hopping. Yeah.
So, hello. Yeah, it's really nice talk. So, I wanted to know about this. Yeah, so you have this 1D SSS model. So you said in the beginning that I mean, in the Hermitian case, the Hamiltonian looks Hermitian, right? You're saying you are performing some analytical in the Hermitian case. So how is it like helpful?
The thing is that we have so we will have 4 by 4 matrix, okay, and we can make it into a 2 by 2 matrix, sorry, such that it is a block diagonal. Each block is non-Hermitian. Each block is non-Hermitian, right? This block is Hermitian to this, but each block is non-Hermitian. So we now diagonalize this non-Hermitian matrix itself and found a criteria analytically how to then using that as a to block diagonalize the full matrix.
So can you say that I mean like one Hermitian and like bigger matrix like 4 by 4?
I think that for an even by even cases it sorry.
Can you say like it is actually kind of two non-Hermitian system can be actually mapped to?
I think yeah, it is very interesting actually. What we found, the main thing is that Hermitian systems, for example, our fermions and bosons, it has to be Hermitian matrices. And one of the thing is that normalization constant for, let's say, the fermions, A dagger A plus A dagger equal to 1, that constant has to be satisfied. And we found that this non-Hermitian matrix allows A dagger A if something, and it is exactly 1 over E. 1 over, so if it is a, for example, 0.8, it is 1 over 0.8. So I believe that this method can be investigated further to see whether that is there. That yeah.
One more, so like you had like in one case you had like 4 age modes and like.
It could be 4, 2, yeah.
So like in one SSS mode. One day. So like if you have the 2 age modes at 1A, so like I mean like can they actually combine and form a normal fermion?
No, they are specialized. They are specially very delocalized. At a given site, exactly there are 2 edge modes. Oh, but they belong to different eigenstates. So they will never. It is on topological origin. So they will not. Topological protection is there. Yeah, you want.
I think the comment to your question that even if you have two boundary modes, even they cannot mix because the origin of these two modes is different band gap project in the parameters. They are not coming from the same band gap project. Yes.
Yes, so the one band, yeah.
Especially in your the spin texture that you have got in your second one, so this persistent spin texture itself there also have some topological character.
So different chart numbers are there as we allowed the A to A hopping, and yeah, we have a topological phase diagram also and corresponding spin structure also. For example, this is the topological phase diagram. Various topological phase 1, 0, 0, minus 1, all topological phase can be obtained. Yeah.
And I can differentiate them by the my textures?
No, actually the spin texture does not, it looks like even for the non-topological the semiconductor system, it does not have special connection with that. Yeah.
Okay, I have one question. You changed your hoppings to many, I mean, next
to nearest neighbor.
How reasonable is that?
That's why I am telling, in electronic, in material, real material, it may not be that that logical, but in artificial material it is possible. And let me, maybe I forgot to include that note. It should have been there. I can show you one reference. Yeah, it is in there. Yeah.
It's fine. I'm just curious.